see, Isaac Newton brought out his book on optics. At that time, he spelled it as OPTICKS. And he wrote, are not the rays of light very small bodies, particles, corpuscles, emitted from shining substance? And he derived Snell's law from that. But this was in 1687. But in 1637, 50 years before, René Descartes had put forward the corpuscular model. And there is a paper saying that he derived Snell's law. But no one gave credit because Isaac Newton's optics became very famous. It was extensively used. So we still believe, we still say that the particle model of light was put forward first by Isaac Newton, but that is not correct. So Isaac Newton and many others got credit for so many things. One other example I thought I would tell you all, this is known as Newton's rings. And you all must have done this experiment. You put a plano-convex lens on a glass plate and you see that beautiful rings, which we do in our undergraduate laboratory. It was first observed by Robert Hooke. So Newton's rings were first observed by Robert Hooke in his 60s, and he described this in a 1666 book on micrographia. Newton gave a wrong explanation for that in terms of the particle model of light, but everyone worshipped Newton, hero worshipping. So it was named as Newton's ring. The correct explanation on the basis of wave theory was given much, much later in the 19th century by Thomas Young. Then, around the same time as Newton, Huygens, as you all know, had put forward the wave theory of light. He said light was a wave. Wave is the propagation of a disturbance. But no one believed in Huygens. Because Newton had said it is particle model. Everyone believed in Newton rather than Huygens. So what is a wave? As you all know, the simplest example is if you hold a string, make it move up and down, then you generate the string, each point of the string oscillates in the x direction, and you produce an x polarized wave. And this equation defines a wave. So the displacement of the string is given by this equation. So this is the wave. The propagation of a disturbance along the string without the string moving forward. And if you write this down, if you take the k outside and then plot it at t equal to 0 and t is equal to delta t, then the whole displacement has moved by a distance of v delta t in a time delta t. So that you plot the displacement at t equal to 0 and at t equal to delta t, and you find that the whole displacement is shifted by a distance v delta t, where v is defined to be equal to omega by k. So this is the definition of v. So therefore v is the velocity of the wave, which I have just now shown to be equal to omega by k. This you all do in your high school these days. So you can have a bipolarized wave also. If you oscillate the string in a horizontal direction, you have a bipolarized wave, which is given by this expression. And then you can generate this on a string, as you must have done, and get it reflected, and you produce the interference pattern. These are the stationary waves. And there are very beautiful video clips on the internet, on YouTube, which you can see, and formation of the stationary waves on a string. So this is now 2-point sources, 2 needles on the calm pool of water. Each generates waves and they interfere, and they produce this beautiful interference pattern. There are regions where they interfere constructively to produce bright, and then there are regions like this line where there is zero intensity. So this is a this phenomenon of interference is a characteristic of the waves. So this is an actual experiment with water waves. So you have a calm pool of water, you have two needles which is vertically going up and down, each producing waves, and then the waves interfere and forms an interference pattern. So therefore, if one needle moving up and down produces a displacement like this, the other produces a displacement in the opposite direction, then the two will cancel and produce zero intensity. Now that is the principle of superposition. And this results in the interference pattern. You can have a circularly polarized wave. If you rotate the string in a circular direction, then each point of the string moves on the circumference of a circle. And if I rotate it in a clockwise direction, you have a right circularly polarized wave. And as for an electromagnetic wave, the electric field at this point will rotate on the circumference of a circle. Understand this? The electric field at this point will rotate on the circumference of a circle. So that is a right circularly polarized electromagnetic wave. So, although the wave theory was put forward by Huygens, it was Thomas Young, as you all know, did this famous interference experiment in 1801. It was a very simple experiment. He used sunlight to fall on a plate, so he made monochromatic light fall on two holes, not two slits. And he pierced two holes on a cardboard, on a screen, and then allowed the light waves emerging from that point to interfere, and he saw straight line interference pattern. So these are not two slits, two holes which produce almost straight line interference pattern. Actually the interference pattern are hyperbolic. But if you look at the small portion of that hyperbola, they are straight line. And he could say light plus light would produce darkness. And therefore light must be a wave. So this is the famous experiment, thought experiment, that Feynman has very beautifully described in his book on Feynman lectures, that you have particles like the bullets coming out of the gun. That is his words, Feynman's words. And you have two holes or two slits. The bullets will either go through hole number 1 or hole number 2. So they are thrown from the gun at random direction. They ricochet from hole number 1 or hole number 2 and arrive on the screen. If hole number 1 is open, then you get an intensity pattern like this. If hole number 2 is open, you get an intensity pattern like this. If both holes are open, then the bullets are either passing through hole number 1 or hole number 2, and you get P1 plus P2. No interference. So bullets either pass through hole number 1 or hole number 2. But if you have a wave source, as I just now mentioned, then just like two needles going up and down, each source produces its own wave and they interfere. And so therefore the points at which the interference pattern is out of phase, it will be zero intensity. Where they are in phase, there will be maximum intensity. And it leads to the interference pattern. Beautiful interference pattern, as you see on the string that I had showed you, or on water waves. So Thomas Young saw those interference patterns. And this is actually Max Born spoke that his experiment showed that light plus light can produce darkness. And so therefore light is a wave. He calculated the wavelength using this formula, which is beta is the fringe width, d is the distance between the two poles, and capital D is the distance between the two screens. So he measured wavelength, and he found that the wavelength of, say, yellow color or something like that was about half of a micron, which was very small. So it is difficult to obtain such interference pattern. But he did observe them. In fact, Thomas Young is said to be the last man who knew everything. The last man who knew everything. Thomas Young, he was a medical doctor, the anonymous polymath who proved Newton wrong, explained how we see, cured the sick, deciphered the Rosetta Stone. The last man who knew the entire physics was Enrico Fermi. And people say that the last man who knew the entire theoretical physics was Lev Landau and Richard Feynman. So, Thomas Young is the last man who knew everything at that time. So light was a wave that was established in the earlier part of the 19th century, but how would it propagate through vacuum? Because a wave requires a medium. So as you know, concept of ether was all-pervading medium was established. Now we know that the ether does not exist. But at that time, theory of ether was there. There has to be something which allows the wave to propagate from one point, which propagates the disturbance. There has to be something. During that period, early 19th century, the laws of electricity and magnetism were getting developed. So you have this, you have a magnet in a coil, and this changing magnetic field produces a current. Changing magnetic field, this is Faraday's law. Faraday discovered that law, and Maxwell put it in the form of a vector equation. So this is known as Faraday's law. It cannot be derived. It's an experimental law. So he wrote that down in the form of an equation. And then there was another law, that Ampere's law, that a current, a conductor carrying current produces a magnetic field. And what Maxwell did was, he put that in the form of a vector equation. Curl of A is equal to J. That a current passing through the conductor produces a magnetic field. Then Maxwell did something remarkable. He modified Ampere's law, as all of you would know, and he introduced that not only a current produces a magnetic field, but a changing electric field also produces a magnetic field. Like the plates of like the field between the two plates of a capacitor. So he introduced this term in an ad hoc manner, the concept of displacement current. So that was Maxwell's greatest contribution. No, his greatest contribution was something else. And so he wrote down these laws of electricity and magnetism in the form of 4 equations. The entire classical electricity and magnetism, or classical electrodynamics, are just solutions of Maxwell's equations and nothing else. And Maxwell's equations are experimental laws. They cannot be derived. I must mention one thing. The concept of field, what is a field, was introduced by Michael Faraday. He said that when there is a charge in vacuum, it produces a field, so that if you put a charge here, it will experience a force. But that field existed before the charge is put. So that this is something like, so the concept of the electric and magnetic field was introduced by Michael Faraday. But the laws of electricity and magnetism in the form of 4 beautiful equations were followed by Maxwell. So these are the rigorously correct Maxwell's equations in free space. And using this equation, Maxwell derived the wave equation. Maxwell derived the wave equation. And he said that the electric and magnetic fields satisfy the wave equation. And so therefore there must be, he predicted the existence of electromagnetic waves. And he predicted that the velocity of the electromagnetic waves So he said that of these equations you have solutions like this. So this, as I mentioned before, represents a wave. And corresponding to an electric field, there is a magnetic field. So you see, from Newton's laws, if you apply on a vibrating string, this is given in any book on mechanics, you can derive this equation. But y is the vertical displacement, x is along the length of the string, and you can derive this equation by applying Newton's laws to a vibrating string. As soon as you derive this equation, you can predict the existence of transverse waves on the string, and whose velocity will be equal to v is equal to under root of t by rho. So therefore, Maxwell derived these equations. He compared with the three-dimensional wave equation, and he said that the velocity of these waves in vacuum will be 1 over under root of epsilon naught mu naught, and using the main values of electric and magnetic constants, he found that the velocity of the waves was 300 million meters per second. And he said this value is close to the velocity of light measured by piezo. And he said that these two numbers cannot be accidentally equal. And so therefore, with faith in rationality of nature, he said light must be an electromagnet. So understand the logic. Understand the logic. He derives the wave equation for electric and magnetic fields in vacuum, and therefore he says that electromagnetic waves must exist. He calculates the velocity of the electromagnetic waves and finds that the velocity of the electromagnetic waves in vacuum is about 300 million meters per second. He then says this is very close to the velocity of light that has been measured by piezo, and so therefore light must be an electron. This is considered to be one of the greatest revolutions in the history of the development of science. So in free space, for example, you have this Faraday's law. If you assume a wave-like solution, you get the corresponding, you substitute it here, take the curl of this equation, and then integrate with respect to time, you get this. So therefore, a light source generates an electric field, an oscillating electric field. The oscillating electric field generates an oscillating magnetic field, and it is the fields which propagate through empty space. It is the fields. A changing electric field produces a changing magnetic field. A changing magnetic field produces a changing electric field. That is how the disturbance is propagated in free space. So this is around 1864 that Maxwell predicted the existence of electromagnetic waves and so on. And God said, let there, this is what Feynman said, God said, let there be Maxwell's equations, and there was light. So this is the entire electromagnetic spectrum, from gamma rays to X-rays to ultraviolet to radio waves to waves that you receive on your cell phone. They are all electromagnetic waves of different wavelengths, as you all know. And all wavelengths travel in free space with an identical velocity of 299792458 meters per second. And the visible region of the spectrum occupies, as you all know, a tiny portion of the electromagnetic wave. This was verified experimentally by Heinrich Hertz in 1887. He used an antenna to produce the electromagnetic waves, an aluminum reflector to reflect it, and he produced stationary waves just like you produce on this string. And he calculated the velocity of these electromagnetic waves, and he found that to be about 3 into 10 to the power of 8, 300 million meters. So Maxwell's electromagnetic theory of light was established experimentally in 1887. And I should mention, I should have had a slide. Jagadish Chandra Bose also made phenomenal contribution in Calcutta around 1891 and 1892, and he generated electromagnetic waves, millimeter waves, and he designed a large number of antennas and did some incredible work there. So Max Planck said Maxwell's theory remains for all time one of the greatest triumphs of human intellectual endeavor. And in 1894, before the turn of the century, electromagnetic theory, as you all know, would explain the reflection of light, transmission of light, why mirror is reflecting, why water has 4% reflection, everything. So there is nothing new to be discovered in physics now. All that remains is more and more precise measurements. Then came Einstein. The year, of course, the concept of the quantum was discovered in 1900 by Max Planck. And then came Einstein. You see, what Max Planck did was that you have a cavity, and the oscillators of the cavity can be treated like a linear harmonic oscillator whose energies are quantized. And what Einstein did was the following. So Einstein, as you know, was in a Swiss patent office, and in 1905 is known as the Annus Mirabilis. Annus Mirabilis are Latin words meaning year of miracles. And in that year of miracles, he published 5 outstanding papers. This was his PhD thesis of measuring molecular dimensions, how big is the water molecule. The second paper, third paper actually, not the second. Third paper, Einstein gave a theory of the Brownian motion, which involves movement of a big particle by continuous collisions with many smaller molecules of a gas or in a liquid. And in the fourth paper, he put forward the special theory of relativity, which implied that time is not absolute. And in the fifth paper, he introduced E is equal to mc square. And in the second paper, it is Year of Miracles, March 1905, he said light radiation energy consists of indivisible quanta of energy. He introduced the concept of the light quantum. E is equal to h nu, and the momentum of this light quantum, and because of this momentum you have these optical tweezers, is h nu by c. So this he introduced in 1905, this I think came in 1908. This was a revolutionary concept. He himself said that. This was a revolutionary concept, and which eventually led to and this is the beginning of wave particle duality. So he introduced that light consists of tiny packets of energy, not as a wave, tiny packets of energy. And he himself could not believe that. He explained the photoelectric effect experiment. Many books write that he developed the photon concept to explain the photoelectric effect. That is not correct. He had calculated the entropy of a light contained in a box and compared with the entropy of a monoatomic gas, and from there he got the concept of the light quantum. And then he used the concept of the light quantum to calculate the maximum kinetic energy of the emitted electrons from a photoelectric surface when an ultraviolet light hits it. So he derived this equation that the maximum kinetic energy of the emitted electron is equal to h nu minus a constant which depends on the property of the material. These are known as photoelectrons. And this was verified with a tremendous degree of accuracy by Robert Millikan. But even then, although Robert Millikan had verified this experiment, no one really believed in Einstein's photon model. Albert Einstein received the 1921 Nobel Prize in Physics not for his theory of relativity, not for the concept of the light quantum, but for explaining the photoelectric effect. And then in 1923, Compton did the famous scattering experiment, in which a photon of a very high energy interacts with an electron, and the photon energy gets scattered with a slightly lower energy, slightly lower frequency. And he calculated, as you must have done so, the kinematics of this experiment, using the fact that the energy of the light quantum is hq and the momentum is hq by c, and verified his experimental data with theory. And he found excellent experiment. It was only after experiment of Compton that people started believing that light also behaves like a particle. So the wave particle, so the concept of the light quantum and what is now light quantum known as the photon appeared only after Compton's experiment, after Einstein had got the Nobel Prize. This is the wave particle duality which led to quantum theory. So then, de Broglie in his thesis, 1924, said that this is the expression that Einstein has derived. There must be an equation similar to that valid for electrons. This was his doctoral thesis. And he said that if Einstein's equation is correct, then electrons should also show a wave-like behavior, whose wavelength will be given by h by p. So this was also a revolutionary contribution. And how did he write that? You see, Niels Bohr had given this Bohr model of the atom, and in his paper in 1913 he quantized the angular momentum. He said that MPR must be an integral multiple of h by 2 pi. And what de Broglie did was that he transformed this equation to 2 pi r is equal to nh by mv. So he said that each corresponds to a stationary state. And that's how he justified that a electron of momentum p should have a wavelength associated with it. This was much before the electron diffraction experiments were carried out. So Niels Bohr had come to the Delhi University in 1960. Here is this, I had the privilege of hearing Niels Bohr in 1960, and I was a young man at that time here, and these are Professor Aulak, our teacher. So it was 1924, de Broglie predicted that electrons should exhibit wave nature. And it was verified experimentally, a beautiful experiment by Davison and Germer and G.P. Thomson, J.J. Thomson's son. And here is an experiment, the result of a similar experiment, that this is produced by X-rays, diffraction patterns produced by aluminum foil and produced by electrons. So see the similarity in the pattern. So this particular photograph, this says that the electron and the photon, is it a particle or a wave, whatever it is, they are both similar. By the way, only Davison and Thomson, G.P. Thomson got the Nobel Prize, Germer missed out on that. So the question arises, is the electron a proton or a neutron? A wave or a particle? Is it a wave or a particle? Some books write that sometimes it is a wave, sometimes it is a particle. That is the wrong answer. The correct answer is that, as Feynman says, they are neither waves nor particles. So I have not answered the question. अगर तुम हमसे पूछते हो कि whether it is a particle or a wave, I answer, न तो ये electron, neither it is a wave nor it is a particle. Then you say, so है क्या चीज? The correct answer is, I don't know. Not that I do not know, no one knows. That's a very important point of contact. That's a very important point of contact. So it is described by a wave function psi. So what is an electron? It is described by a wave function psi. And what is this wave function psi? It is the solution of the Schrodinger equation. And where did I get this equation from? The answer, if I say that, you will not believe me. But Feynman writes, this is Feynman. Where did we get that equation from? The answer is nowhere. It is not possible to derive it from anything you know. This is very profound. And next he writes, it came out in the mind of Schrodinger. For example, Maxwell's equations cannot be derived. Similarly, Schrodinger equation cannot be derived. So, in this slide, I have summed up the basic formalism of quantum mechanics. That what is an electron? It is described by a wave function psi, which is the solution of the Schrodinger equation. And Schrodinger equation, where did it come from? It came from the head of Schrodinger, from the mind of Schrodinger. So people have tattooed them on their hand and on their back. Women have tattooed them. So it is said that Peter Debye came to know of de Broglie's result, that electrons should show a wave-like property. And he gave a lecture somewhere in Munich or something like that in 1926, 25 or 26. And he said that there must be a wave-like equation satisfied by the electron. Schrodinger was in that lecture, that is how the story goes, and he immediately wrote down the equation, and in 3 beautiful papers he gave the solution of the hydrogen atom, harmonic oscillator, angular momentum, everything. The entire quantum mechanics was written down in 1926. Of course, the basic paper was that of Heisenberg, but the solution of hydrogen and the Schrodinger equation, of which we spent a major part of our MSc, was written down in 3 beautiful papers in 1926 by Schrodinger. So, let me give you a heuristic derivation of the Schrodinger equation. So, this is a wave, as I had told you in the very first slide that I had shown. And now, somehow in this wave, I inject wave-particle duality. So K I write as P H by lambda, that is the de Broglie relation. I divide and multiply by 2 pi, I get H cross K. So that K is equal to P by H cross. And we also have the Einstein relation, E is equal to H nu. I divide and multiply by 2 pi H cross omega, omega is equal to E by. So this equation can be written down for the electron like this. And for a free particle, E is equal to P square by 2m. So I get so much. So I differentiate once with respect to time, and I get delta psi by delta t is equal to P square by 2m I by H cross minus, and we multiply by I by H cross. So I get P square by 2m psi, and I differentiate with respect to x. These right hand sides are equal. So this is the one dimension. So this is a heuristic derivation. There is no rigor in this. And the solution of this equation. So don't ask me how I have got this. There are a lot of loopholes here, lack of rigor. But somehow I have got this Schrodinger equation. So this is the one-dimensional time-dependent Schrodinger equation for a free particle. And now I take this as my Bible and solve this equation. And as you must have done in your MSc, I use the method of separation of variables. The variables separate out, and I solve each equation, and I get this as the solution. And of course this I will get this as a solution, because this is how I had derived that equation. But now I do not worry about how I have derived. But now that I have the equation, this is the solution. But P is just a number, because in the previous slide, the variables have separated out, and I put that equal to a constant equal to P square by 2m, where P can take any value between plus infinity and minus infinity. And so therefore the most general solution will be a sum of this. So this is known as a wave packet. This is a rigorously correct, most general solution of the one-dimensional Schrodinger equation. So please look at this. If I put t equal to 0, then this term goes out, so I get this. And this is the Fourier transform, Fourier equation. So I take the inverse Fourier transform and I get this. So if I know the wave packet at time t equal to 0, I can calculate A of px from this. I substitute it here and study the evolution of the wave packet. I'll give you one or two examples and then. So this is the wave packet. Max Born said that psi squared dx is the probability of finding the electron between x and x plus dx. And this is the momentum distribution. Apx mod square is the momentum distribution. You write that down in terms of time and frequency. Then delta omega, delta t is of the order of 1. This is classical optics. That leads to the coherence of a packet of a laser pulse. There is a spread of, if you generate a 1 nanosecond pulse, 1 nanosecond Fourier transform pulse, then because of the finite duration of the pulse, there is a frequency spread. And that frequency spread, delta omega, delta t, is of the order of 1. So you can write the electric field also as a superposition of frequencies. Similarly, the wave function is written as a superposition of different momentum. And psi squared dx represents the probability distribution of the finding of the particle, and this is apx mod square represents the momentum probability distribution. So let me do the simple experiment of diffraction of a light. So you do this, the Fraunhofer diffraction, you have a light beam coming from the left. As you all know, it diffracts and the intensity distribution is given by this. You solve the corresponding Schrodinger equation for the electron. And you say that the electron, when it passes through the slit, I know it is for sure passing somewhere through the slit. So psi of x comma 0 is given by this. It is finite here and 0 everywhere else. Then I find apx using this and I calculate this. I substitute it here, calculate the apx and calculate the momentum probability distribution. And I find that this is the same as the classical intensity distribution predicted by my Fraunhofer diffraction. So you see, even if you are, this is very simple physics. The electron, when it passes through the slit, it interacts with the slit imparts a momentum, and there is a momentum distribution. So the probability for the momentum to be between px and px plus dpx is the same as the intensity distribution predicted by my wave theory. So where will the particle land? I cannot predict. I can predict only a probability distribution. So quantum mechanics is a probabilistic theory. Classical mechanics is a deterministic theory. And from this, the smaller the width, greater is the momentum spread. So that the uncertainty is contained in the solution of the Schrodinger equation. Let me do another experiment, the double slit experiment. So as you know, if you have the double slit experiment, you have the intensity distribution on this. Just the first experiment that I had shown, that Feynman's diagram. This is the 2-point interference pattern and this is the single slit diffraction pattern. And we solve the same problem using quantum mechanics. Then the electron is described by a wave function which is present here and here. And then you solve this and find the momentum distribution function and you find it. So that the electron passes through both the holes. It is described by a wave function which is finite here as well as here. So one single electron passes through both the holes, interferes with itself to produce a probability distribution which is the same as the intensity distribution produced by, given by the Fraunhofer diffraction pattern. So J.J. Thomson had discovered the electron, and now we know the mass of the electron to 10 decimal places, the charge of the electron as the 10 decimal places. So how can an electron pass through both the holes? That no one understands. So electron does not split into half and half. It passes through both the holes. So if electron was a tiny particle, if you do this double slit or double hole experiment, then if the electron passes through hole number 1, it produces an intensity distribution like this. Hole number 2, it produces it like this. Then you expect that when both holes are open, it will be either passing through hole number 1 or hole number 2. But what you get is the intensity. So this can be only explained if one electron passes through both the holes simultaneously. But if you make a measurement as to which hole the electron has passed through, then it will be either hole number 1 or hole number 2. And in the process of the measurement, the interference pattern will be washed out. So this is said to be one of the most beautiful experiments in physics that was carried out by many people, but the most sophisticated was done by Tanamura. Single electron experiment. So you send one electron, and the top one is for 10 spots, and the lower one is for about 1 million. So you see, when you have 10 electrons, then you have 10 spots here. And there is no pattern. Slowly, as you build up the number of electrons or number of photons, slowly the interference pattern builds up. So therefore, you have two slates. Understand this. The wave function is the electron, one single electron or a proton or a neutron or an alpha particle or a photon passes through both the holes. It interferes with itself to produce a probability distribution like this. So the electron is everywhere. It is here as well as here. The process of measurement makes it collapse to a particular point. And you get the intensity pattern. So this is the photograph of a young lady with 3,000 photons and 28 billion photons. When you have 3,000 photons scattered from the face of the girl, then you have 3,000 spots. You can only predict the probability. So the most fundamental theory now available is probabilistic in form and not deterministic. Classical mechanics is deterministic. So you see, you do this tunneling experiment, and a particle comes in and interacts with the potential barrier, and then you calculate this reflection coefficient and a transmission coefficient. So a single particle like a neutron or an alpha particle comes in here. It is described by a wave packet which is here and here. The electron is here as well as here. If you make a measurement, then it is either here or there. So you take the single photon source. The single photon source puts in one photon after the other. You have a beam splitter. Then you would say, if there are 1,000 photons coming in, 500 will come here, 500 will go there. That's a wrong answer. One photon is here as well as here. But if you make a measurement, then it is either here or there. So the photon being at both the places collapses to being either here or there. So You have 5 more minutes, kitna there? 5 more, 10 more minutes, 5, 7 more minutes. Then I will finish. All of you have seen a doubly refracting crystal. So, you make a beam enter, it splits up into 2 polarized beams. This is an actual experiment. It splits up into 2 linearly polarized beams. You take a 45-degree polarized beam. Then it splits half intensity here, half intensity here. This is the X-polarized photon, and its polarization is in the vertical direction, and this is Y-polarized, perpendicular to the plane of the photograph, of the page. So if you have a 45-degree polarized photon, say a single photon source passed through a polarized 45 degrees angle, then you produce a 45-degree polarized photon. तो वो कहाँ जाएगा? तो वो यहाँ भी जाएगा, यहाँ भी जाएगा. It's in a superposed state. So it is in this beam as well as in this beam. The process of measurement will make it collapse either here or there. So, so you have something like a calcite crystal. So this is an XY device, and you orient that crystal, and you have a UV device. That is, any light, any polarized light will split into U and V components. I'll just take 5 more minutes. And you will orient the calcite crystal like this so that it becomes sigma eta device. So now, I have a calcium source. It emits 2 photons. If one photon is X polarized, then the other photon is Y polarized. They are entangled. They are entangled in the sense that the polarization of one is at right angles to the other. So when it is passed through an XY device, you know for sure it is X polarized. The other photon collapses to being Y polarized. Before that, you do not know. According to quantum theory, read this carefully. The polarization of the photon traveling to the left or to the right is not known before one of them is measured. If the photon going to the left is passed through an XY device and it is found to be X polarized, then the photon going to the right collapses to a state in which its polarization state is Y polarized. So this Einstein, similarly, if you pass through a UV device, if it is U polarized, then this automatically, you don't have to measure it will be depolarized. I said something very important. Whatever happened to one particle would thus immediately affect the other particle, wherever in the universe it may be. Einstein called this spooky action at a distance. And he said there must be some hidden variable associated. So in 1935, Einstein, Podolsky and Rosen wrote a paper that if quantum theory was correct, then 2 particles, which are billions of kilometers apart, can be entangled in the sense that by determining the property of one of the particles, the property of the second particle can be instantaneously changed. And special theory of relativity forbids the transmission of any signal faster than the speed of light. This came to be known as the EPR paradox. About 30 years later, experiments confirmed the predictions of quantum mechanics. Namely, Einstein's impossible prediction proposition was in fact correct. Instantaneous changes in widely separated systems did occur. देखिए, I have a system which has total angular momentum equal to 0. This is a thought experiment. It emits 1 electron and 1 positron in opposite direction. because it has total angular momentum 0, if I make the measurement of the spin angular momentum, if it is up, then this will be down. If I measure this to be x, then this will be y. This will be opposite, sorry. Before I make the measurement, I know that theory tells me that they will be opposite to one another. But when I pass through this through a Stern-Gerlach apparatus and measure that this magnetic moment is in the upward direction, then the other one will be in the downward direction. It collapses immediately. It may be millions of kilometers apart. And this was very carefully done with light experiments. So EPR argued that if without in any way disturbing a system, we can predict with certainty, that is a probability equal to unity, the value of a physical quantity, then the second particle, you see, this is what Einstein said, the second particle must have possessed the measured property before the measurement was carried out. That is, what Einstein said, but it is something like a green marble and a red marble. I told them, so I said that if this is, I open this red, I do not know which one is red and which one is green. But God knows that this is red, green, and this is red. So he said that there must be something hidden variable, so that it is known. But it is not known. Quantum mechanics tells us that if I measure it to be green, then the other one will be red. It collapses to a state when it is red. So I assume the hidden variable theory, and I ascribe that each photon, if it is passed through an XY device, it will be X polarized. If it is passed through a UV polarized, it will be U polarized. Sorry, this will take a little longer time. So I rather skip. So if hidden variable theory is correct, then it's a very simple analysis. I have done this, many people have done this, even in my optics book, that if the hidden variable theory is correct, then this inequality should be varied. And what does this inequality tell us? The left hand side is probability that the left photon, if it is passed through an XY device, it is measured to be X polarized, and the right photon, if it is passed through a UV device, it is measured as U polarized. And similarly Px sigma and so on. If Einstein's hidden variable theory is valid, then this Bell's inequality has to be satisfied. and see this experiment, that if this is X polarized, then according to quantum theory, the other will be Y polarized, which makes an angle theta with the U axis. So the probability that the right side will be U polarized will be, according to the law of Malus, cos square pi by 2 plus theta. So on, so according to that, if quantum theory is valid, Bell's theory will imply this, and this is, if we assume theta is equal to 2 phi, the above inequality will imply this, for phi is equal to, we will have this, which is an impossibility, Thus, quantum theory and Bell's inequality are not compatible, which implies that either quantum theory is right or theory based on hidden variables, but not both. And this is a very beautiful experiment carried out by Alan Aspect and in which they carry out this coincidence measurement of the photon, 2 photons emitted, and these are the XY device and UV device, and they aspect, right, the linear polarization correlation of pairs of photons emitted in a radiative cascade of calcium has been measured. The new experimental scheme using two-channel polarizers is a straightforward transposition of the EPR thought experiment. The present results, in excellent agreement with quantum mechanical predictions, lead to the greatest violation of Bell's inequalities ever achieved. So Bell's theorem represents as one of the most profound discoveries since Copernicus. Bell discovered a death blow to the local realistic picture of the world. Many experiments have demonstrated that the predictions of quantum mechanics for entangled particles are fully correct, and the world is really as crazy as predicted by quantum mechanics. So, right, if you hear this lecture on YouTube, Feynman's famous messenger lectures at Cornell, and they are now available on YouTube. Electrons do not behave just like particles. They do not behave like waves. Electrons in orbits are not somewhat like a cloud, of fog of some sort surrounding the nucleus. It behaves like nothing that you have seen before. These are his own words. Well, there is one simplification. Electrons behave exactly the same way as photons or neutrons or protons or whatever you may think of. And I think I can safely say that nobody understands quantum mechanics. So you see, quantum mechanics allows you to calculate, but how does the basic concepts of quantum theory can be understood only through experiments like the double hole experiment, as you all know. So, same experiment can be done by using this thing. So, sorry. The angular momentum of the photon has two possible values. Oh, this I must tell you. Plus h cross or minus h cross was first put forward by Satyendranath Bose in a letter to Einstein, which Einstein removed that. So, angular momentum of the photon is h cross plus or minus h cross was put forward by Satyendranath Bose. So, these are the very nice references, the basic references of quantum mechanics, the principles of quantum mechanics by Dirac, and of course Feynman lectures, quantum theory by David Bohm. Each one is an authority on quantum mechanics. Dirac is a Nobel Prize winner, Feynman is a Nobel Prize winner, David Bohm is an almost Nobel Prize winner, and this is by Cohen-Tanuji, is also a Nobel Prize winner. But if you read each of the books, each one has its own way of reaching the Schrödinger equation or the basic concepts of quantum mechanics. What I have, so this is Dirac and Feynman. David Bohm became a philosopher. This is David Bohm, became a philosopher and became a disciple of J. Krishnamurti. If you do too much of quantum mechanics, you become a philosopher. That's what happens to even Schrödinger became that. And here is Cohen-Tanuji receiving the Nobel Prize. Whatever I have said today, I am right now working on the 8th edition, the last 2 years of my book on optics. And this is what the publishers have said the cover will be. And this is the spectacular display of colors in the northern and the southern hemispheres are called aurora borealis and aurora australis. And it happens because of the charged particles that come out of the sun and get trapped in the magnetic field near the north and the south pole, excite the atoms. And in this case, the green color is due to the oxygen atoms. When you see such things, you feel that the study of light is probably the most fascinating thing to do. And this is the double rainbow which I show. When I see this, I feel that this experiment, this is a, so I can go on and on. So I end here. I'm sorry, in the derivation of Bell's inequality, I did it in a hurry because there is a little shortage of time. But I hope I have been able to convey to you the great beauty of quantum mechanics and the fact that we do not really understand quantum mechanics. Thank you very much.